double integral. We take the double integral over R of 1 dA. How do we find the mass using double integral? The mass of an area, of course, that would be the double integral over the region R of the density dA. Rho is density. Okay, how do we find volume using double integral? Yes, it's not strange. We can find volume using double integral. So the volume using double integral, I need to be more specific. This would be the volume under z is equal to fxy. So we have z equals to fxy, which is the surface. We're talking about the volume under the surface over the region R, and the region R is in the xy plane. So you have a surface, and you're finding the volume that's under the surface over a certain region in the xy plane. That would be volume is equal to the double integral over the region R of fxy dA. How do we find the volume using triple integral? The same way as we use area for double integral. So the volume would be the triple integral over the region E of 1 dV. That gives us the volume of the region E. Right, so it's the triple integral over a region of 1 dx dy dz. That gives you the volume of this region. Now, how do we find the mass of a volume? So the mass of a volume using triple integral. Of course, same thing as in area. Mass is equal to the triple integral over the region E of the density dV. Always when you want to find mass of a volume, you multiply the integral of volume times the density. Mass of an area, you multiply the integral of the area times the density. Now, how do we find the center of mass and versus the centroid? So I'm going to explain to you what center of mass is and what centroid is. Centroid is basically just the center geometrically. So that means the density is equal to a constant. Here, the center of mass, the density isn't a constant. So let's look at the case that is 2D. Again, I'm giving you all the possible formulas that we could encounter, and then we're just going to spend the rest of the time practicing. So in 2D, so we have the center of mass, which is x bar, y bar. And the centroid would be just x bar, y bar. So what's the difference between center of mass and centroid? Let me just draw you an example to explain the difference. So let's say you have a rectangle made of wood or lead or something. You have a rectangle with constant density. Where would be the center of mass of this rectangle? So here, if it's the constant density, the center of mass will be here. Let's put it in red. And let's put the centroid in blue. Right, the centroid and the center of mass will just be the same if the density is constant. If this is constant density. So the geometrical center of the object, blue is just the geometrical center of the object. Red is the center of mass. So where is the mass, sort of the center of the whole mass of this? Now, let me show you a different example. Let's say that you have the same rectangle, but now this half is made of feather, and this half is made of lead. Okay, where would the centroid be? The centroid wouldn't change. The centroid would still be here. Because centroid doesn't care about mass. Centroid is the geometrical center of the object, so the centroid stays exactly where it was. But now where would the center of mass be? See, the center of mass would be more skewed toward the lead part. Because the lead part would be much heavier than the feather part, so the center of mass would be more skewed toward the heavy part. It doesn't really change anything. So for 2D, for centroid, you take x bar is equal to the double integral over the region R of x dA over the area, which is the double integral over R of 1 dA. Again, this is the area. And for y bar, you take the double integral over R of y dA all over the double integral over R of 1 dA. Again, these are just the area. If we were talking about center of mass, then x bar, you have to involve mass now. So the double integral over R of x density dA over the mass, which is the double integral over R of rho dA. This is the mass, right? And y bar, that would be the double integral over R of y rho dA over the double integral over R of rho dA. Again, if we knew that the mass is this, then we could just divide by m. This is the mass m, where the mass, well, I gave you the formula for that. Okay, now if we're doing objects in 3D, right? Centroid doesn't really care about mass. So centroid, you would get x bar is equal to the triple integral over the region E of x dV over the volume, which is the triple integral over E of 1 dV. I'm just going to be lazy and I'm going to duplicate it 3 times. So now, sorry, this doesn't change. So y bar and z bar. So y bar would be the double integral of y dV, and z bar would be the double integral of z dV. If we were talking center of mass, so we would have to divide by mass, which is rho dV. And we would need a rho in each one of those integrals. Again, this is the center of mass, and this is just the centroid, where it's the geometrical center. This, all of these, this, and this, those are the mass. And this, and this is just the volume. And these are literally all the formulas. Volume, mass, area, anything that we encounter will be on this page. The trick is now to just practice. So let's practice. We're here to practice. So let's look at 2019, let's say, question number 6. Here we go. Let's practice. The time is now to just practice. So we're going to practice, and then we're going to practice changing bounds and triple integrals. It's just going to be more and more different exercises to practice the whole thing. So this is from 2019. A solid is bounded by the cone z is equal to the square root of x squared plus y squared, and the plane z is equal to 1. So we have a cone, z is equal to x squared plus y squared, right? So this is going to be the cone. And z is equal to 1. So z is equal to 1, so it's the plane z is equal to 1. So this is the z-axis. This is the y-axis. This is the x-axis. Right, so this is the plane, z is equal to 1. So the cone is basically cut off at z is equal to 1. And we know that the density rho is the square root of x squared plus y squared. By the way, square root of x squared plus y squared, sometimes they put it as the distance, sometimes they call it the distance from the axis of the cone. Basically r, guys. So how far a point is from the axis of the cone. And the square root of x squared plus y squared, if you transform it into polar, you're just gonna get r. So what's the mass? So this is the region E that we are talking about, right? So the mass of this region is the triple integral over that region E, which we're gonna learn how to parameterize, of the density dV. So what's x doing, what's y doing, what's z doing? Now the easiest bit is what z is doing. What's z doing in my region? Z goes from this to this. Can you see that? Z goes from here, from this to this. Anywhere in the region, Z goes from here to here. So Z seems to be going from the cone, from the square root of x squared plus y squared to 1, to Z is equal to 1. Remember, how do we find volume when we're talking in 3D? We have a surface on top of a surface, and this is all happening over a region in the xy plane. So the xy plane give us like a region, and z goes from one place to the other, just like areas where we did the area is the top curve minus the bottom curve. Here we're doing a volume, so the top surface minus the bottom surface over a certain region in the xy plane. And to get the region in the xy plane over which all of this is happening, right? To get the region in the xy plane over all of this is happening, just eliminate z. Remember this. So to get the region in the xy plane, eliminate z. Basically find the intersection. So you're gonna get z is equal to the square root of x squared plus y squared, and you're gonna make it intersecting z is equal to 1. So that means the root of x squared plus y squared is equal to 1. That means x squared plus y squared equals to 1. So that means this in the xy plane, the region in the xy plane over which this volume is happening, over which z is changing from the bottom surface to the top surface, is this. This is x squared plus y squared, technically less than or equal to 1 because it's a region. So in the xy plane, if you just look at the xy plane, what's the region shadowing this is this. The x squared plus y squared equals to 1. And can this be more polar? It's incredibly polar, right? So we can take theta going from 0 to pi to 2 pi. And r literally goes from 0 to 1. So when you do, by the way, when you do polar in triple integral, it's called, it has a name, it's called cylindrical coordinates. It's just a name, it's a way to call it. So it's called cylindrical coordinates. So let's write it down. The mass is equal to r theta z. So cylindrical coordinates are r theta z. So polar with a z. So theta goes from 0 to 2 pi. R goes from 0 to 1. Z goes, we have Z, and this is equal to R. Z goes from R to 1. The square root of x squared plus y squared, that's R. And dV is going to be R dr d theta dz, right? Because when you move from dx, dy, dz, when you move from dx, dy to polar, you're going to get r dr d theta, and then dz just stays dz. So that's the mass of your object. So this is the integral from 0 to 2 pi, the integral from 0 to 1. Sorry, this is dz dr d theta. This is z. dz dr d theta. I messed up my order. So z, then r, then z. So the integral of r squared dz, that's r squared z from r to 1, dr d theta. The integral from 0 to 2 pi, the integral from 0 to 1. So this would be r squared minus r cubed, dr d theta. The integral of r squared is r3 over 3 minus r4 over 4 from 0 to 1 d theta. So this is 1/3 minus 1/4. So this is 1/12 d theta. So this is 2 pi over 12. So the mass is pi over 6. Right? So that's how we find a volume. Well, a mass technically. So which is a volume times a density. Okay, let's pick another equation before we get to Cartesians and changing of bounds and whatever. Let me ask you one that's a little bit harder. In fact, you know what? Let's look at the 2022. Remember, I told you 2022. I didn't interchange the order. I was hoping we can get a nice integral on this. Do not disappoint us, 2022. Okay. So this is a center of mass. There is no triple integral in here, unfortunately. There's this one, but here we go. I was wrong. I take it back. There was an integral in 2022. I thought I saw one. I doubted myself for a second. So let's solve this one together. Let E denote the region lying below the paraboloid this. So below this, so this is the top. This is the bottom. So you automatically have a range for Z. They're gifting you the range for Z. And you want to find the volume of E. They're telling you to use polar coordinates, but you'll see it'll be very, very clear that you should. So paraboloids, by the way, are like parabolas all the way around. So this is the top paraboloid. Let's say it looks like this. And this is the bottom paraboloid. So they gave us the top paraboloid, which is z is equal to 4 minus 2x squared plus y squared. It's like an Easter egg. So z is equal to 2 minus below the paraboloid, above the paraboloid. So in fact, both of those are like this. And both of those are paraboloids like this. One of them will hit here at 4, one of them will hit here at 2, by the way. the graph looks like this. Like, right, both of them are a parabola. You have a narrow paraboloid and you have a wide paraboloid, and they will intersect like this. So I hope I've made this a bit clear. So this is the volume that we're trying to find. So the top paraboloid is this, the bottom paraboloid is this. Doesn't really matter. In this case, you don't technically need a graph. In this case, theoretically, a graph is useless because you can see what's happening on the z-axis. You know which one is the top and which one is the bottom. And you know that the intersection over the xy plane, so what's happening in the xy plane, is going to be the shadow of the intersection. So this is the region D or the region R in the xy plane. Can I give you 30 seconds to set this up? The volume is equal to the triple integral over the region E of 1 dV. We know the range for Z. I'm going to let you write it. Then you need to find the region R in the xy plane, and then write bounds for R. Seriously, please, please, please try this on your own to see if you actually understand what I'm trying to tell you or not. Multiple integration takes a lot of practice. Unfortunately, this is not like the tangent planes where I show you how to find the tangent plane and that's it. You know how to do it, whatever curve they throw at you. Unfortunately, this takes some practice on your own. It's the nature of things. Not me, not Einstein can, make you do this. You have to try it on your own. So we know what the range for Z is. Z goes from the bottom one, 2 minus x squared plus y squared to 4 minus 2x squared plus y squared. Now, they told us integrate with polar, so really let's not be, let's just write it right away as 4 minus 2r squared. Is this part okay? Because you've been silent for a while, and I've been talking to myself. At least, is this part okay? Because they tell us which one's the top, which one's the bottom. Okay. How do I find the intersection of these? How do I eliminate Z to get to what is the region in the XY plane where I'm going to make them equal? Thank you, Brooklyn, for telling me. So we have 4 minus 2x squared plus y squared is equal to 2 minus x squared plus y squared. Well, let's keep solving in terms of x squared plus y squared. So 4 minus 2 is equal to 2x squared plus y squared minus x squared plus y squared. So we get x squared plus y squared equals to 2. So the region in the xy plane is the disk of radius root 2. Fantastic. So theta goes from 0 to 2 pi. R goes from 0 to root 2. Z goes from 2 minus R squared to 4 minus 2R squared. We are finding the volume. So 1 dV is R, dz, dr, d theta. Let's not forget the R. Ta-da-dum. So this is equal to, again, you're going to finish this. So this would be the integral of 1 dz r z, and then z is from 2 minus r squared to 4 minus 2r squared dr d theta. Anyway, they gave you the solutions to these so you can check the answers. All right, let me ask you a slightly more difficult one. So let's ask you a slightly difficult one. Find the volume of V bounded by Z is equal to 4 minus 2y, Z is equal to 4 minus x squared minus y squared. And in terms of k, given that the integral from sine to the 4th theta d theta is equal to k. We need bounds here. I didn't copy the bounds into the question, but we will figure out what the bounds is once we solve this. Actually, let's make it 0 to pi. So now this is a little bit more difficult. We need to figure out how does this volume look like. See, z is equal to 4 minus x squared minus y squared. We know that it's a parabola. So if this is the z-axis, this is a parabola. It goes like this. Right? So it's a parabola. And it starts at 4 right here, and it just keeps going down as a parabola. Now, what if z is equal to 4 minus 2y? So if this is the y-axis, this is the x-axis. Of course, y is equal to, z is equal to 4 minus x squared minus y squared. We'll go through y equals to 2 here. When it touches the xy plane, when z is equal to 0, it's going to be x squared plus y squared is equal to 4. So it's going to touch 2. But now z is equal to 4 minus 2y. It's this plane. It's this plane right here. Come on. It's this plane right here that extends on all sides. So the volume is this. Now, I'm going to attempt to draw it for you. You have a paraboloid like this, right? But then you're cutting it off by a plane. So technically, you're going to have a form that looks like this. It's so difficult to draw in 3D. Do you see what I'm saying? This is the plane. This is the plane. Z is equal to 4 minus 2y. And this is the paraboloid that's going down. This is the paraboloid. Z is equal to 4 minus x squared minus y squared. Do you see my volume better in this image? So you have the paraboloid going down, and the plane is just cutting it off like that. So Your range for Z is not a problem. As always, at Queens, they don't make the range for Z very difficult. If you, I mean, you don't need to do like a nice drawing like this. You could have just kept it like this. It's clear that Z goes from the plane to the parabola. The issue is not with Z. The issue is over what region is this happening in the XY plane? So what's the region in the XY plane? Now, you will discover that the region is those special circles I talked to you about. But how do you discover this? So what is the region R in the XY plane? Because as I said earlier, the range for Z is pretty clear. We know that Z is going to go from 4 minus 2y to 4 minus x squared minus y squared. There's no issue with the Z. Now, how I'm going to give you a minute to do it on your own. How do I find my region in the XY plane? My question to you is, what's R? So, what's R, ladies and gentlemen? Well, we got to eliminate Z. So 4 minus 2y is equal to 4 minus x squared minus y squared. This tells me that x squared plus y squared is equal to 2y. Do you remember this? We talked about this when we talked about nice polar curves. We talked about this. And if you forgot what that we talked about this, then write it down as x squared plus y squared minus 2y equals to 0. Complete the square, so you're going to get x squared plus y minus 1 squared is equal to 1. And you'll see right away that it's a circle with center 0, 1, and of radius 1. So the region in the xy plane is that region we talked about. It's the center 0, 1, and this is the radius 1. So that's what's happening in the XY plane. Of course, from here, we could have also gone x squared plus y squared is equal to 2y. So r squared is equal to 2r sine. Simplify by r, so r is equal to 2 sine theta. So that's my region. And that's why I gave those regions to you earlier, because I knew they would show up on questions. So theta goes from 0 to pi when r goes from 0 to that curve, which is 2 sine theta. So what's my volume? My volume is theta from 0 to pi, r from 0 to 2 sine theta, and z from 4 minus 2r sine theta to 4 minus r squared, 1 r dz dr d theta. So now the integration is a little bit annoying. Let's go and do a couple of steps, not all of it. Hopefully we get to something that's simple. The integral of r dz is rz. So then I'm going to put the bounds for z right away. R 4 minus r squared times r 4 minus 2r sine theta. You can see that this integral is a little bit annoying. So this is the integral from 0 to pi, the integral from 0 to 2 sine theta. This is 4r minus r cubed minus 4r plus 2r squared sine theta. 4r minus 4r is gone, dr d theta. So this is the integral from 0 to pi. The integral of r cubed is minus r to the 4 over 4 plus 2r3 over 3 sine theta from 0 to 2 sine theta. Oh, look how cute this is. The person who asked this question is very nice. So when I put 2 sine theta, this is going to give me minus 16 sine to the 4 theta over 4 plus 2 over 3 sine to the 4 theta d theta. Now that this would be minus 4 plus 2/3, so minus 12 minus 12 plus 2 minus 4 plus 2/3, so minus 10/3, the integral from 0 to pi of sine to the 4 theta d theta, and they gave us this to be k, so the answer is minus 10 over 3k. Da-da-da-da. I think this question is quite nice. So, are we getting these? So, right, let's, I want to leave the triple integral till after the break. I want to check if there's like a nice problem we can do. Let's do 2021, see what they had. Again, those are the two finals that I did not take questions from. I left them till, here we go. You see, that's 2021. I always like to do some questions like fresh with you guys. Not that I solved the other ones, but I like make a list of other ones. How did I find the bounds for R? Not a problem, Ruben. R starts at the origin and it goes to this curve. Anywhere you draw R in your region, it goes to this curve. And what is this curve? This curve is R is equal to 2 sine theta. Makes sense? And how do I get R is equal to 2 sine theta? Because I have x squared plus y squared is 2y. So x squared plus y squared is R squared. And y is R sine theta. And then I simplify an R on each side. That gives me R equals to 2 sine theta. So the circle of center 0, 1 and of radius 1 is the circle R is equal to 2 sine theta. So R starts at the origin, always, 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 and it goes through the region. And the maximum R we get is the R that's in R equals to 2 sine theta. Makes sense? Okay, shall I give you a second to set this up? This is a nice question from 2021. Take 30 seconds to set this up. By the way, the session for 174 starts tomorrow. The on-demand component will be posted for 174 like sometimes tonight, I think they told me. I finished it and I sent it. I solved a lot of problems in that 174 on-demand part. And I made it so that almost like 99% of the problems I solved were not solved on the midterm. I tried to pick completely new problems to make it more interesting and more useful to you guys. So the session for 174 is tomorrow. So use polar coordinates in the xy plane to find the volume of the solid bounded by the plane and the paraboloid. Well, this paraboloid is a paraboloid that starts at the bottom, right? So it starts like this. And we have a plane z is equal to x that's just going to cut it, right? So there's a plane z is equal to x that's just going to cut this, but actually z is equal to x will cut it like this. So it's a part of the parabola that's going like this, and then it's being cut by z is equal to x. So why am I doing this? Because it's pretty clear the range for z now, if you see this. So z is going to go from x squared plus y squared until 2x. The eternal question is, what's the region over which this is happening in the xy plane? So what is the region R that's in the xy plane? By now, this should be somewhat straightforward to you that we cancel z in both. So that's going to give us 2x is equal to x squared plus y squared. Do you recognize this? This is x squared plus y squared is equal to 2x, which means r is equal to 2 cos theta. So the region in the xy plane is the circle that is centered at 1, 0, and of radius 1. That's r. So theta goes from minus pi over 2 to pi over 2. And then r, Ruben, like last time, it starts at 0 and it goes, the outer part of this is the curve 2 cosine theta. So the volume is the integral from minus pi over 2 to pi over 2, the integral from 0 to 2 cos theta, the integral from r squared to 2r cos theta of 1 r dz dr dθ. So this is the integral from minus pi over 2 to pi over 2, the integral from 0 to 2 cos theta. The integral of r dz is rz, but then I'm going to put the bounds for z right away, 2r cos theta minus r squared, dr d theta. So when I integrate with respect to r, that'll give me 2r squared, so 2r3 over 3 cos theta minus r3 over 3. Nope, minus r to the 4 over 4. From 0 to 2 cos theta. And when I put r is equal to 2 cos theta, that would be 8. So 16 over 3 cosine to the 4 theta minus 16 over 4 cosine to the 4 theta d theta. So this is 16 over 12, which is 4 over 3, the integral from minus pi over 2 to pi over 2 of cosine to the 4 theta d theta, and they gave us the integral of cosine to the 4. So that's right. Is this okay? I hope you know that we've done enough problems of this to get you sort of in the right mindset. But please, 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 this is not enough. You really have to practice on your own. So go to those finals that I've given you, go to the practice and practice, 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 practice. Please, it's very important to practice a lot. So that leaves us with triple integrals and changing bounds. So the last thing that we haven't done is triple integrals in Cartesian, of course. So with respect to changing bounds, changing the order. And that's a little bit annoying, but again, we're going to do as many problems as we can to make it less and less annoying. It's time for our break. So I don't think we need to add the 5 minutes from the last break. Can we just make this a 20-minute break? So right now it is 8:15. Let us be back at 8:35. And then from 8:35 till 9:30, we are going to do triple integrals, changing the order, and take whatever questions that you have for me. And that completes our series and our integration. Of course, if you have any particular questions, please let me know. All right, so see you in our last break in 20 minutes. Hey everyone, we are back. So, let's see. We were going to do triple integrals in Cartesian involving change of bounds. So let's practice. Let's see. So let E be the volume. So here's an example. It's in one of the finals. I just can't remember which final I took it from. So let E be the solid that is in the first octant. First octant means the positive x, y, and z. Bounded by BDD, bounded by 2x plus y plus z is equal to 8. So that's the plane. 2x plus y plus z is equal to 8. Y is equal to x squared, which is a vertical cylinder. And x is equal to 0 and z is equal to 0. So this would be x equals to 0. This would be the yz plane. And z is equal to 0. That would be the xy plane. Let's find the volume. Now let's write the integral that gives the volume. So we want to write the integral that gives the volume, and then we're going to change the order. We're going to write this in a couple of different orders. So let's see. We want to write the volume first. First of all, let's just draw this. The question in the exam said to write the volume as E of dz dy dx. So we're going to do this, and then this is in part A, to write the volume in this. In part B, they ask us to change it to dy dz dx, so to change it to dy dz dx. And in part C, they asked to say dy dx dz. So it's a nice exercise in changing the laws. Let's first understand what's happening in this drawing. So unfortunately, and I say this like with all the love in my heart, you really have to draw. And I get it, drawing in 3D sucks. I still, I'm not super excellent at it even after so many years, but you got to do what you got to do. So it's bounded by the YZ plane. So this is going to be the back of it. This is going to be the XY plane, right? And then we have the region 2x plus y plus z is equal to 8. So if x is equal to 0, we're going to get y plus z is equal to 8. So the plane looks like this in the YZ plane, where this is 8 and this is 8, right? So if I take x is equal to, if I took the plane 2x plus y plus z equals to 8, and I made x is equal to 0, meaning in the YZ plane, I get y plus z is equal to 8. So this is the y plus z is equal to 8. Now, there's that cylinder y equals to x squared. Y equals to x squared looks like this, right? But it continues on the other end, but we don't care about the other end. Now, the plane also 2x plus y plus z is equal to 8. When z is equal to 0, we're going to get 2x plus y equals to 8. So it's going to be a line, it's going to be a line that looks like this. It goes until 4 here. So, and there's that cylinder, right? That just is a vertical cylinder. So it's gonna touch here. So the cylinder will just be like this, right? So the volume is bounded by, and I'll do it in purple, the whole object. is bounded by the plane. Here is the plane. By the cylinder. This is the cylinder on the side. And by the xy plane and the yz plane. So this is the back of it, and this is the bottom of it. So there's a lot of moving parts in this, but it's not so bad. Okay, so let's see. First, in part A, of course, let me copy this. Let me copy this because I'm going to need to work with it 3 times. So in part A, I want dz, dy, dx. So x is on the x-axis, y is in the xy plane, and z is in space. Cool. So let's try this. Where does x live on the x-axis? So this is y equals to x squared. This is y equals to x squared. And it's intersecting this line, which we said is 2x plus y equals to 8. So this is when x is equal to 2. You can check that. This is when x is equal to 2. So on the x-axis, my x's go from 0 to 2. That's for the whole volume. So x is from 0 to 2. Again, how do I get the 2? It's the intersection of 2x plus y equals to 8, intersecting with y equals to x squared to find out what this point gives me on the x-axis. Now, for my xy, for my y, I'm going to look only in the xy plane. So I'm looking here. What is my y doing? It's difficult to draw straight lines and all of this. What is my y doing? Y is going from x squared to this line, which is 8 minus 2x. You can see it clearly right here that it's 8 minus 2x. Now, what is my z doing? Z starts at the floor and it goes up to the plane, right? This acts as a side, right? This is a vertical cylinder, so this is a side. It doesn't, Z doesn't hit it. It's just Z starts at the bottom and it goes to the ceiling, which is the actual plane. So Z starts at 0 and it goes to the plane, which is 8 minus 2x minus 1. To the plane, Z is equal to 8 minus 2x minus 1. Okay, let's do this one more time, but in a different order. So now we want the order dy, dz, dx. Now we want the order dy, dz, dx. So x is still on the x-axis. Now z is going to be in the xz plane. So we're going to have to draw some nice graphs. And y has to be in space. Very nice. So we know that this point is x is equal to 2 now. We talked about this. So x goes from 0 to 2. That has not changed. Okay, what's happening with z? Remember the trick we did before? To get into the xy plane, we eliminate the z. To get into the xz plane, we eliminate y. So to get the shadow of what's happening into the xz plane, so there's like a shape like this, right? So this is x is equal to 2. But I want to figure out like what's happening here. And if you want to guess it, it looks like this. If you had to guess, there's a shape that looks like this. But I want to find what this is, because this is where Z lives in the XZ plane. But I want to find the equation of this. And to get the equation of this, we did like we did before, we eliminate the y. So we have y equals to x squared, and then we have y is equal to the actual plane is y is equal to 8 minus z minus 2x. So when we eliminate the y, we're going to get 8 minus z minus 2x is equal to x squared, which means z is equal to, move it to the other side. Wow, this is a lot of negatives. Minus x squared minus 2x minus 8. That's bizarre. No, plus 8. I apologize. So it's 8 minus 2x minus x squared. So this is z is equal to 8 minus 2x minus x squared. So in the xz plane, z goes like this. It changes, z changes from 0 to the curve 8 minus 2x minus x squared. How did I get the 8 minus 2x minus x squared? Again, I eliminated the y's. I got rid of the y's. So I got an equation that links z and x, which means it's an equation in the xz plane. Now, what's y doing? Now in space, now we have to look in space. Y starts at this end of the volume and goes to this end of the volume. Right, so it's pretty clear that y goes from the cylinder x squared to the plane, which is y is equal to 8 minus 2x minus z. That was a lot of fun. Let's do one more order. And now we want to dy, dx, dz. dy, dx, dz. All right. So z is on the z-axis. X is in the xz plane. And then y is in space. So y is still the same as before, right? Since y is still the space one, we know that y will just be the same. So I remind you that this point is at 2. That here we have a curve that we found earlier. And the equation of this curve is z is equal to, come on, 8 minus 2x minus x squared. And they're being annoying in this, but whatever, it happens. So on the z-axis, z goes from 0 to 8. No problemo there. Now, in the xy plane, what's x doing? X is changing like this. So x is going, no, we don't want to use this, we're going to use green. So x goes from here to here. So x goes from 0 to this curve. But then how do I get x in this curve? The first time you see this, it's shocking. The second time you see this, it brings back memories. So how do I get x in this curve? Anybody wants to tell me? Well, I got to do the quadratic formula. So I'm going to say x squared plus 2x plus z minus 8 is equal to 0. So x is equal to minus b plus or minus the square root of b squared minus 4ac all divided by 2n. So if I want to simplify, I can say plus or minus. I can factor the 4 and put it out. So that would be the square root of 1 minus z minus 8 over 2. I can cross out the 2's everywhere. So minus 1 plus or minus the square root of 9 minus z. Now, which is it? Is it the plus or is it the minus? Is it the plus or is it the minus? It's definitely the plus because that's the positive x, right? So it's on the side that's positive x. So this equation, x is equal to minus 1 plus the square root of 9 minus z, because this is a parabola that looks like this. So here it's the breakpoint. This is where x is negative. This is where x is positive. So you want this side where the x is positive. And voila. The first time we did this, it was terrible. Now we do it and we don't even think about it. That's a normal thing to do the quadratic formula. Right? Okay, let's look at one. I wrote, this is another one. I wrote assignment 4 of last year, but I don't know if you had the same assignment or not. I wrote like do this from assignment last year in my notes that I prepared. So I don't know if you have the same assignment or not, it doesn't matter. So they tell us that the volume E is given to us by y is bigger than or equal to x squared. 0 is between, z is between 0 and y. X is between 0 and 1. And y is between 0 and 1. And the density, rho is equal to z. They ask us to write the mass integral. So we're going to write the mass integral with dz, dy, dx. And part B with dy, dz, dx. So that's fun. So let's try and draw this volume and then see if we can, once we draw it, finding the bounds won't be a big deal. But the problem is drawing the correct region. So z is equal to y is a plane that looks like this. So you get z is equal to y, but then it just extends, right? Then it's just it's a plane, like it's a sheet of paper that extends everywhere. Come on, sheet of paper. Right, so it's a sheet of paper that's just lying on these x-axis, and then it just goes everywhere. So we're going to keep that in mind once we draw things. This is y equals to x squared. Again, there is the other side, but x is only between 0 and 1, and y is only between 0 and 1. So x between 0 and 1, that means if we stop here, our volume, like our area, will stop here. We'll also stop here. So that would be y equals to 1. But then there's this item on top, right? So we gotta go up until we get to a certain point right here. So we're gonna have a plane like this. Like there's a side like this. And then right here, we're gonna go to the top, which is z is equal to 1. Right, and we're gonna have a shape that looks like this. You see this? So this is the plane z is equal to x, which is this surface. This whole surface is the plane z is equal to x. And this is the side y equals to x squared, which is technically like a cylinder that looks like this, right? Y equals to x squared, but then it's just an infinite sheet of paper. And then x is equal to 1, y is equal to 1. So when x goes from 0 to 1, y goes from 0 to 1. Z is between 0 and y is bigger than x squared. So it's this object right here. So this with this, with this, with this, with this, with this, and then with this. Very exciting. So let's copy it because we're gonna do work on it twice. So let's do first dz dy dx. X is on the x-axis, y is in the xy plane, and z is in space. You see how my poem really helps? So on the x-axis, we can see it right away. X goes from 0 to 1. In the xy plane, we're here. So in the xy plane, y is going from y equals to x squared to y equals to 1. So y is going from x squared to 1. And in terms of space, z starts at the bottom and it goes up till this plane. So z starts at the bottom and it goes to z is equal to 1. So if you want to write the mass integral, this is the integral from 0 to 1, the integral from x squared to 1, the integral from 0 to y of the density z, dz, dy, dx. Fantastic. Let's say, for example, let's say they add, so this is extra. Let's say they ask you for the formula for y bar of this of the center of mass. So what's the formula for y bar? Remember, it's very simple. So you divide by m, and in the integral where you have m, you simply just put an extra y in there. So this would be z, y, dz, dy, dx. Right? So, for example, if they wanted this. Now, the next part is a lot more interesting. We have this, and now we want dy, dz, dx. It's interesting because x is still on the x-axis, no problem, but z now is on the xz plane, and we see nothing in the xz plane, like it's empty. So I gotta fill it up. I gotta figure out what's happening in the xz plane, and then y is in space, so no problem. So what's happening in the in the yz plane? X is pretty clear. X is going from 0 to 1. So let's not worry too much about this. X goes from 0 to 1. I need to figure out what's happening in the xy plane and in the xz plane. And this is going to be a little bit tricky. Please pay attention. Look, if you shadow this point back to the xz plane, if you shadow this point back to the xz plane, I'm going to shadow it right correctly. You're going to get the point right here where it's z is equal to 1 and x is equal to 1. It's important you try and do like the best drawing possible, right? So this is z is equal to 1, and this is the point where z is equal to 1 and x is equal to 1. But then when you shadow, now I need to figure out what's happening inside that region. So I'm going to eliminate the z, the y. So I have y equals to x squared, and I have z is equal to y. So this is y equals to x squared, intersecting z is equal to y. So if I eliminate the y, that gives me z is equal to x squared. Z is equal to x squared is this curve right here. So I'm going to take this away so you can see. This is Z is equal to x squared. The problem is my volume fills the entire region. Like it's not above or below the line. My volume, if you look at it, like this thing right here, this rectangle right here, if you shadow it to the XZ region, it covers the entire Z region. So why am I worried about this curve Z is equal to x squared? Because, pay attention, and this is why this is hard. I'm going to break this up into a green region and a yellow region. When I am in the green region, y goes from this curve to y equals to 1. When I am in the yellow region, y goes from x squared to 1. So it's a different range for y. So when x goes from 0 to 1, great. But then I got to break it up into two areas. When z is from 0 to x squared, so that's the yellow region, y goes from x squared to 1. And when z goes from x squared to 1, that's the green region, y goes from z, y equals to z is equal to y. I don't know why I said z equals to x. This is z is equal to y, to 1. So I have to write it down as two integrals. And again, the first time you see it, it seems like overwhelming and difficult, but then you learn how to deal with cases like this. Right? So as I said, I am going to give you some extra change of bounds, a lot of changing bounds, so you can re-practice this. And if you have questions, you could always ask me. Like, see, this seems to be a similar problem. So I have solved a few more problems like this, so they're very, very interesting. While I was on the break, I was looking at a problem, and it's a difficult polar problem. Do you want me to do? I'm basically done. So I was gonna do a difficult polar problem, and maybe like a centroid, or if this is not okay, I could do one more example of these. I leave it up to you. If you ask me, I think you should see the difficult polar problem, because I mean, this you've seen, and I have given you extra practice for this. The polar problem is like nothing you've seen before. It's a little bit more difficult. So polar it is. Nobody is saying anything. So this is an extra polar question. And it's a little bit difficult. So the volume E in R3 is above Z is equal to 2 minus 2x minus 2y, and it's below Z is equal to 2 minus x squared minus y squared. So there's no confusion as what's on top, what's on the bottom. And R, so R is the region in the xy plane below E, under E. So part A is to sketch R. Part B, to write the integral for volume. Cool. So how would I find the region in the XY plane. By now we've seen this, we just eliminate Z. So to get the region in the XY plane, we're gonna do 2 minus 2x minus 2y is equal to 2 minus x squared minus y squared. So move everything to the other side. X squared minus 2x plus y squared minus 2y is equal to 0. See, it's one of those circles, but it's not on the x or the y-axis. So here you have to complete the square in both. So you complete the square here by doing plus 1, plus 1. You complete the square here by plus 1 and plus 1. So this gives you x minus 1 squared plus y minus 1 squared is equal to 2. So my dear friends, the region in the xy plane is the circle that is centered at 1, 1 and of radius root 2. So when you do this, it goes like this. The radius is root 2, so it's got to go through here. Sorry. I'm getting a little tired with this, so let me do a better drawing. Radius 1, 1. Sorry, the center 1, 1 and of radius root 2. So it will go through the origin. That, my dear friends, is your region R in the XY plane, and that's why I'm doing this question. I don't know if they're going to ask you this. This is from a final in 2014, but that's basically the region R. Now, we agree that if we want to write the integral of the volume for part B, I need to parameterize it. Like, I need to find the bounds for R. So what is theta doing and what is R doing? You see, R is simple. R starts at the origin, and anywhere you go in the region goes to this curve. It goes to the curve. So R starts at 0 and it goes to that circle. So we need to find the equation of the circle in polar. Now theta starts here. I don't know what this is. And it goes all the way till here. Right? Theta goes from this theta to this theta. The question is, how do I find theta 1 and theta 2? You see why this is interesting? So, first of all, the equation of a circle, one task at a time. So for the equation of the circle, we're going to go back to x squared plus y squared is equal to 2x plus 2y, which we get from here. X squared plus y squared is r squared. X is r cos, y is r sine. So if I simplify by r everywhere, I get r is equal to 2 cos plus 2 sine. So that's the equation of this circle in polar. Great. How do I get theta 1 and theta 2? So how do I get theta 1 and theta 2? The idea is that theta 1 and theta 2 happen when r is equal to 0. So when r is equal to 0 is when I'm getting theta 1 and then theta 2. Those are the values of theta that make r equals to 0. So when do I have 2 cosine theta plus 2 sine theta equals to 0? That's when sine theta is equal to minus cosine theta. So that means when tangent theta is minus 1. So we know that this is now minus pi over 4, and this is 3 pi over 4. So tangent is 1 or minus 1 at pi over 4s, right? Tangent is 1 at pi over 4 or pi over 4 plus pi. So that's how I get the bounds for theta. So if I want to find the volume, theta goes from minus pi over 4 to 3 pi over 4. R goes from 0 to 2 cos theta plus 2 sine theta. And then Z goes, well, Z, we have it here. It's above this and below this. So Z goes from 2 minus 2r cos minus 2r sine. And it's below this, so below 2 minus r squared. And it's 1r dz dr dθ. Clearly, they're not going to ask us to evaluate this. It's hell. But they could just as well ask us to write it down. And ladies and gentlemen, that's the whole idea. Again, and one last time, multiple integrals are about the domain of integration. So you figure out your domain of integration, everything else is just a formula. So everything else, centroid, mass, volume, whatever, all of them are just formulas. The idea is you want to figure out what your domain of integration is, and from there on, everything is very, very simple. That's multiple integrals, ladies and gentlemen. I'm waiting for your questions. So I gave you a whole bunch of tests. I think from 2015 or 2014 to 2019, they gave you a bunch of tests also from 2020 to 2022. That's a lot of nice exercises. And we know that Queen's doesn't go far from past finals. Like, it's new questions, it's interesting questions, but never like a question. I mean, maybe one question that's completely weird, but the vast, like the big part of the test is just similar to previous year. Is there anything else that you'd want to ask me? Of course, if you don't ask me now, you could always ask me later. Anyway, some of you, most of you, I should say, are watching on video. So you could always email me at antoine@prep101.com. I should let you know that this weekend is incredibly busy for me. I am having double sessions Friday, Saturday, and Sunday, and Monday, actually. So if I'm slow to answering you, please don't think I'm ignoring you. I'm just literally stuck in a session. So as soon as I can, I'll take some time every night to answer the students' questions. Anything at all? Well, thank you for coming. Thank you for your trust. 174 is tomorrow. I don't know if you're in 174 or not, but we start 174 tomorrow. Thank you so much for everything. In the next 3-4 minutes, I'm gonna make sure the notes is posted for you and you have access to them. I wish you a fantastic night. Good luck on this and all your finals. Head office, thank you very much. And I shall see you during our next session. Bye, everyone.